Hello, good morning, and welcome to this almost last session of this wonderful symposium. Today we have two parts of the session. The first part with 3 presentations is about the LIGO-Virgo-Kagra collaboration, a huge project on ground and their experiences regarding visibility outreach, and another future project, Cosmic Explorer. Then after the break, we will have 2 presentations from our friends and colleagues in China about the Tianjin and the Taiji project, and about future ideas to go in space with missions beyond Visa. The first presentation is by Livia Conti from INFN in Italy about LIGO-Virgo-Kagra collaboration and some questions regarding presentations and visibility. Please go ahead.
Yes, okay, let me share the screen. Okay, yes. Okay, so hello everyone. So my name is Livia Conti. I am a researcher at INFN in Padova. And as I said, I am a member of the Virgo collaboration. And today I want to talk to you about the issue of visibility of Virgo, and more recently also of Kagra in the scientific literature. In summary, the issue of the visibility of the LVK. And this is the list of people who have collaborated to this work. And we are all part of the LIGO-Virgo-Kagra collaboration. So this is the outline of my talk. So I will start by explaining to you what we mean by the issue of the visibility and why we care for it. Then I will discuss our approach to solve this problem and at least how to mitigate it. And so I will present some results and conclude with future work. So let me start with some history, which many of you already might know. Anyway, in 2007, LIGO and Virgo, who are ground-based gravitational wave detectors, have agreed to join in a collaborative search for gravitational waves. And since then, they have operated as a sole machine, a single machine, and the major results have been developed and co-authored by both the collaborations. And this wider collaboration has been joined in 2020 by Kagra, the ground-based Japanese detector for gravitational waves, and this realizes the worldwide network of gravitational waves. And this is what we call the LVK collaboration, LIGO-Virgo-Kagra. And in principle, and in the intention of the scientists, this is a collaboration among peers. However, this is not always recognized in the wider scientific community and as well in the media. And an effect of this lack of recognition is that the collaborative work and the results that are achieved by the collaboration are not attributed correctly. So let us be more precise and state a little better what we mean by this problem of the issue of this problem of the visibility. So the problem we want to address is that the contribution of Virgo as a collaboration and as a detector is not fully recognized in the scientific literature. And what we observe is that when discussing gravitational wave discoveries and results, in the text of some papers, people refer systematically to LIGO, where instead LIGO-Virgo or LIGO-Virgo-Kagra should appear. And I want to stress that this is not a problem of missing citations, but we are concerned with the narrative of the scientific developments. That is to say, on how science is told. In other words, our concern is not if Virgo papers are cited, and they are cited, but rather if Virgo is placed correctly and it is associated with its science in the text of the articles. And more recently, a very similar issue appears also concerning Kagra when citing results from LVK collaboration papers. So here I make a couple of examples of what I'm talking about, and these are our starting points, so where we started from. The first paper is a paper by the Gravity Collaboration, which is an influential paper, and it has made some impact. And in this paper, we find sentences like the ones that I put here, in which they only mention LIGO, the LIGO black holes, and the LIGO measurements. The second paper is a less known paper. But again, we have this issue with the events only attributed to LIGO. So it is clear that there is a problem. But why do we care for this? We care because we believe that this biased narrative can produce a detrimental effect, both in the short and the long term. And the scientific community should be able to associate Virgo and now also Kagra to gravitational wave discoveries and science. And these bias impacts have several impacts. So in particular, impact affect badly the work of hundreds of people at work at LIGO, at Virgo and Kagra, and in particular on the career of young scientists. And it also has a bad effect for defending agencies. And in the end, this is also reflected on how we are represented in the media, and hence has an impact also on the wider public. I want to point out that we have raised this issue in front of the Virgo Collaboration first about 1.5 years ago. Then in March this year, we've raised this to the LVK Collaboration. And in both cases, we have received large and positive feedback from our colleagues, meaning that this issue is felt as important by the whole LVK Collaboration. And now let's see how we tackle this problem. Our idea is to give feedback to the authors of papers that show a problem. So we send them an email where we explain the problem, and we show where the paper contains an issue. And we ask them to edit the paper and fix it. Our goal is not only to fix the specific issues in that specific papers, but rather to educate the authors. And by doing this, we aim to educate the scientific community by doing this in over an extended amount of time. And this is in more detail our workflow. So we have a script that automatically checks the papers that are posted every day on the archive. We focus on GRQC and AstroPH. This script produces a list of possibly problematic papers. Then these papers with the warnings are checked by volunteers, so people from our group, in bunches of 1 week. And then we send an email to the authors to ask the authors of really problematic papers to edit their text. And sometimes there is an email discussion with the authors to explain our viewpoint and our work. And this is it. Let's see some results. In 2011, we started this process, but not in a well-organized way. A more systematic approach has been taken since the start of this year, thanks also to the fact that we have more volunteers. And our aim is to cover all the weeks of the year, and we are already progressing well. So this is the results from the first 7 weeks of January, starting from mid of January. The scripts have processed 4,000 papers, and we found 600 which cite LIGO, and among them 200 have some alerts, and these are those that we manually inspect, and among these we found 40 papers with major issues. So about 7% of the papers who cite LIGO show some really big issues with the visibility. And in average, we found 6 papers per week to have major issues. And the authors of all such problematic papers have been reached by our email. But we have not done this only for these 7 weeks, but we have, in this year, we have already analyzed papers from 27 weeks, so all weeks starting from mid of January. And manually, we have scrutinized 800 papers that have appeared on the archive. And we found 212 papers with serious issues. And so these papers we sent emails, and in average we found 8 problematic papers per week. Of course, these are the papers that have just appeared on the archive, so we are not assessing the real impact of the papers. So, of course, the papers who attract many readers and many citations, so influential papers, will contribute more to spread the same misconception. So, but we treat all the papers at the same level. Again, some results: about 17% of the authors which are contacted by us are reply, and I'll give you later some examples of their replies. And usually they understand the issue, and they express the willingness to edit the papers at the next occasion. However, we are not following up the papers to see if the changes that they promised are actually implemented. So this is something we don't check. This I want to give you, since there is a short time, I want to give you just a few examples of papers with issues, and I want to give you here to show a change in the paper that was achieved after our email. So in this paper, they showed a table with data from the first catalog of gravitational wave transients, and which was referred as LIGO only catalog. And then after our email, this was changed into LIGO Virgo correctly, recognizing the role of Virgo. And here are some more examples, but anyway. And here I want to give you some ideas or some examples of replies that we have received. So I will not read all of them, but just give you, I have highlighted in red the most important parts. So the first 2 replies indicate that people do not really know the real contribution of Virgo. So I thought that the original pre-2017 papers were just signed by LIGO. And also this expression. So this, they don't know the real contribution of Virgo. The replies from 3 to 5 show that people are aware, but somehow fail to fully recognize the role of Virgo. And the last 2 replies support our idea that doing this work, we do educate people and not just fix the scientific papers. So this is a hope for the future that we are in the right direction. Then to get some results, as I said already, we need to educate the community and not just a few people, so the few authors. So we estimate this process needs to be continued for at least about 1 year. So this time is we estimate enough to survey a good fraction of scientists which are active in our community, scientific community. As a future work, and this is my concluding slide. So I want to say that awareness on this issue is increasing and is already high within the LVK. The LVK after March, following in the past few months, have decided to to put in action some more, to put in practice some more actions to solve the problem. And among these additional actions, we want to inform the editors of major scientific journals so that they can check how the LVK is referred to when they proofread the articles. We want also to contact the managers of preprint repositories such as Inspire and Archive to change the way our papers appear when cited from their database, because this is sometimes also the way we are cited and makes an issue, so can bias the readers. And we want to identify, and we have identified a unique acronym for being cited, and we want to explain what the LVK collaboration is. Okay, and this was my talk, and thanks for your attention.
Thank you very much for this very important talk about this very serious issue. And thank you also for staying on time. That means we have now 4 minutes for questions and discussion. So please type in the chat or just raise hand and unmute yourself. Yes, please, Martin.
Yeah, thanks, Gerhard. Thanks, Livia. Very nice talk. I have a kind of a comment and a question. The comment is partially wearing my chair of the advisory committee hat, because some people may be thinking, well, what's this got to do with Lisa? And for me, the project you've been leading is potentially quite important in the sense that Lisa is a joint ESA-NASA mission. And I think it demonstrates that you know, we need to be clear with other scientists and with the public on what that means. You know, we don't want, for example, the public to get the impression this is just NASA or indeed just ESA. And it's good to see that if you take proactive steps, then you can achieve some good results. So that's my comment, a long comment, sorry, but the question is rather shorter. And it's just to ask, how long do you think we will need to be proactive like this to really, you know, make a kind of permanent change in the scientific community, so that we no longer need to check so carefully, and because we can trust that they will always refer to LVK. Do you have a sense of that?
Well, no one knows, I think, but we as said, we think that we need to push this effort at least for 1 year. So the idea is that in 1 year, it's a time between one paper and the next one of the same author, let's say. Obviously, things changes, and we will need to check. And I cannot, I don't know the exact answer, but at least 1 year, I would say.
At least 1 year. Yeah, thank you.
Yeah, thanks for the comment about Lisa. Indeed, this was the reason for giving the talk to this audience.
Yes, that's very relevant indeed.
I don't know if you have already experienced or you are already experiencing this.
Well, more in outreach than with other scientists, but in outreach, I very frequently get, oh, that's a NASA mission, isn't it? And it's just because NASA is such a recognized global brand, you know, there's not really much we can do about it, but your project demonstrates that we can do something if we are proactive.
Everybody's writing in the chat. Currently, Lisa is an ESA mission with NASA participation. Yes, indeed.
Forgive me, Oliver, I was using a bit of shorthand, but you know what I mean. You know, that absolutely demonstrates that we need to be careful that the public don't think of this as a NASA mission. I will defer to others.
Martin, absolutely, I know what you mean. And I don't mind calling it an ESA-NASA mission, not at all. It's just because of exactly the problem that NASA has a much bigger pull in terms of PR and public recognition. We need to be, I'm hesitant to say careful, because the clear way forward there is not to trying to minimize the NASA pull on things. It is to maximize the ESA kind of outreach and being available or being visible to the world. It is a somewhat uphill battle, I can tell you, as probably everybody who worked with ESA outreach will have experienced. We simply don't have the resources that NASA has, but we've seen that in other missions, where despite the fact that it's an ESA mission, it's usually considered a NASA mission. I mean, SOHO is a good example, and yeah, I think we have to fight that a bit.
Thank you. We have to move on. The next presentation from Hannah Middleton about what's called the LIGO magazine, maybe just in point. Please go on.
Hi, everyone. I'll just share my screen. Okay, hopefully that looks all right. Yes, so I'm going to talk about the LIGO magazine. And this is a presentation also with Anna Green. So our plan is to have a run through this presentation and then have like a discussion afterwards. So I'll run through the slides and then Anna and I will answer any questions. And I also see there's Sasha obviously online, and I saw Suzanne and Paul too. So there's lots of editors who are available to answer questions. So the point of this talk is that the LISA community is recently, or the Outreach team has been starting to think about whether they'd like a LISA magazine. So we were here to sort of share our experiences of working on the LIGO magazine. Okay, so as an overview, this is, I'll say what it is and why bother having it, basically, why it's a valuable resource. And then a little bit of our experience of how the editorial team works, and then what you can read inside of a typical issue. So, so it's a twice yearly publication by the LIGO Scientific Collaboration. And I know what we were discussing just now with Livia. It's true that this is a LIGO is a LIGO publication, but we also include updates from Virgo and Kagra authors as well. It's free to download and read, so the website is here. And it is aimed at both the gravitational wave community and the public. So we're performing two tasks here. We want to educate ourselves about what is going on in the gravitational wave community. So as an example, I work on data analysis. I know very little about what's going on at the instrument and on the experimental side. So it's to educate ourselves. But we also want to inform the public of what's happening in gravitational wave science. And we've recently joined Twitter, so you can follow us as well. So what can you read about? So the LIGO magazine includes personal stories. So it's like the inside story of people working on the science, their personal perspectives and experiences. We have news and discoveries, and these are often reported by early career researchers. Advice for and by early career folks, and engagement activities from around the community, and more things. So this is by the community and for the community. And why bother? So why have this magazine? So we really want to emphasize these personal stories. Like, scientists are people are working on these massive discoveries, and it's the stories of people waking up in the middle of the night to go and check on gravitational wave alerts. This kind of what is it like being a scientist, basically. It also presents opportunities for early career researchers to present their take on the big results. So we have early career researchers talking about the catalogue papers, the big discoveries, the latest work at the sites on commissioning and the technology improvements. And we also want to share news from inside and outside of our collaboration. So the updates at the sites, as I say, but also from beyond. So from the LISA community and pulsar timing array community. So the gravitational wave community as a whole. And also to highlight these outreach and public engagement activities. There's so much going on, and to highlight this, I think, is really valuable. So how is it used? Like, once you've got this resource, it's useful for us as a community. We can learn about each other, learn about the collaboration. And I won't read all of these, but it's used in many different forms. So obviously for outreach, people take them to outreach booths and give them out to folks who are interested in gravitational waves who may not have, sort of as general public audience, and visitors to departments, our own students, and also government officials. So Dave Wright here said he used to go up to Washington to meet with government officials and would give a magazine to these junior and senior staffers. And I also particularly like this one from Eduardo. So this is for our own perspective and current students. So I think that finding a community is important to students, and the magazine is pretty good at describing our world. And of course, we point the online version to as many places as we possibly can. So in social media, blogs, outreach events, talks, and anywhere you can advertise it. So I'll say a little bit now about how the editorial team works and sort of our experience of producing a magazine. So they're all volunteers from the LIGO community, and it's led by an editor-in-chief, which is me at the moment, and a deputy editor-in-chief, which is Anna. The team meets online a few times per issue, but the majority of the work is actually done via email and instant messenger. And we work closely with Sasha and Milda Science Communication for the layout. So this lecture, the layout is professionally done. This is what our website looks like too. So in terms of actually publishing an issue, we normally start about 5 months before the publication date. And this is sort of getting in touch with authors, deciding which topics to cover. And it's published during each LIGO Virgo Kagra meeting. So this is really a hard deadline. So it has to be there at the meeting. And so I guess if the LISA community is thinking of having a hard deadline like this, my advice would be to build in plenty of contingencies. And it can be a little bit of a balancing act, because sometimes articles have to be delayed because they're either too long to fit in the page count, or they're not ready in time, and we have to print on time. So some sort of general thoughts on building the editorial team. I think it's important to aim for a mix of perspectives and seniority. So try and represent your collaboration through the team, both in terms of having early career researchers, perhaps senior folks, to the topics that you cover. So what are these people working on? You don't want it just to be people working on the instrument, or just people working on the data or the astrophysics. You want a range, and different institutions as well. And I think this is a good aim for the team, but also a good aim for the article content as well. And it sort of grows naturally because you have people who know what's going on in different areas. It works very well when individual editors are proactive. So you need to sort of keep the ball rolling with authors and keep good communication back and forth with the team. And you also need people to take responsibility and follow up with folks to get the issue out on time. And this is basically just loads of emailing. Okay, so I'll go back to the magazine itself and just say a little bit more about how it's formatted. So it's 36 pages long. We have a high quality design for PDF and print. And we print, so it's obviously free to just read and download online from the LIGO website. And we do a limited print room of 500 copies. And these are distributed between the observatory sites, the meeting venues, and a few institutions. So we try to share them out as best we can. And the magazine is supported by the Max Planck Institute for Gravitational Wave Physics, AEI, and Caltech as well. So I'm almost at the end. So this is the typical issue sort of format. We have a few long articles, which is like, could be 4 pages or more. And these are like feature articles of the latest commissioning updates, or the latest upgrades to the detector, the latest results, the big discoveries. And in the most recent issue, we had several pages on the catalogue results coming out. And then we have several shorter articles, which can be all sorts of things, and several regular features. So normally we have a LISA update, some little quick read explainers, which are often illustrated by Natsini Kibunshu, a work after LIGO feature where we catch up with folks after they've who were previously members of the collaboration on like a wide variety of jobs that they're doing now. We have advice for and by early career researchers, and a news piece where people can anyone can submit a short career update or news story from themselves. So in the latest issue, this shows what we've covered. So many of these regular features. To the LISA update, our explainer was how do cryogenic detectors work, and we had a really nice article on class discrimination in academia. So we're trying to also cover these sort of socially important topics in science, as well as people's personal perspectives of working in gravitational wave. Okay, so this is the last slide I have. So in summary, I personally find, but this is a lot of fun. I think it is a lot of work, but we find it really enjoyable. And I would say most of all, the advice would be to have fun with it, be creative, and try and to make something that's fun to read, fun to produce. And just to advertise the September issue, we'll be celebrating 10 years of LIGO magazine in September, so watch out for that online. And yeah, that's all I have. And I think Anna and I guess the other editors online can also answer any questions that you might have.
Thank you. And please excuse me for forgetting to introduce Anna Green as second speaker of the yes, a question, please. Andrew, you had raised your hand, but that was maybe not a question. We have 8 minutes for discussion, and I think there's a lot of things to discuss.
Simon here. I can't raise my hand. I don't know why not, but I could speak.
Please.
Hi. Obvious question. How do we copy this for LISA? How do we get funding within the LISA project? How do we find the awesome people doing all the work?
So I think that we can answer in terms of finding the people to do the work, but in terms of the funding, I think this is something that probably needs to be discussed internally for LISA. I guess for finding the people, you should look for people who are enthusiastic about it, and both in terms of the editorial team and the writers as well. And I mean, I think it's a case of like, if people are doing interesting stuff and people are having interesting experiences all the time, we just need to ask them to write their stories down. And people don't necessarily realize that what they're doing is like something that would be cool to read about in a magazine. They just think it's their day-to-day, but it's like those stories are really out there. So Anna, I think.
Yeah, I was thinking maybe we can say a bit about the size of the team you would be looking for as well, because that can maybe seem intimidating when you're starting from scratch. So I think obviously Hannah and I are kind of leading and trying to find editors and this kind of thing at the moment. But the core editor team would be, you know, maybe 3 or 4 very active people per issue, and then the editorial team would be maybe order 10, something like that. And then finding people to actually write the articles, that then comes from either you hear something that you want to know more about, and so you seek out someone that can tell you about it, or you know someone through the grapevine, that kind of thing. And so the levels of commitment that is needed by those team members vary quite drastically and can be quite flexible, and should be.
How good is the retention of the team? Are people dropping in and out constantly, or do you have like the core team that is on there for years and years?
Yeah, so there's a few different durations, I guess, that people would have. So you can look maybe the editor role. We're now on the 3rd editor. So those tend to be the longer serving things. And then we have some members of the editorial team that have been on since day one and still are, and have contributed more and less at different phases through that. And then we have some new editors that have just joined and they're having their first issue now. Maybe they will stay for 1 issue, maybe they'll stay for the next 10, who knows.
Cool. Thank you. Stefano?
Yeah, thank you. Very interesting talk. Just maybe I missed it. Is this a full-time job for the two of you? And
No.
what fraction of your working time is?
Well, I think for me and Anna, it takes a good chunk of time. We're both postdocs, right? So we're doing it in our like besides our research.
Yeah, so the entire team is voluntary, but at least within LIGO, we're starting to be a little bit better about saying, okay, how are we contributing to the collaboration? And then this becomes part of our work as members of the collaboration, but we don't have a specific allocation or pay from this.
Yeah, I was following on the question from Simon, right? If we have to find dedicated people that do this as their only job, that would be difficult. But if you can do as, say, 20% of your time, that's different, right? Thank you.
Yeah, the workload also varies dramatically as you go through each magazine cycle. So I think right now, Hannah and I are reaching the busy phase, trying to pull all of the early drafts into final things that are printable. But there's some downtime just after each issue is released when you can just do your research.
Thank you.
More questions? There's a comment from Martin Henry. It's recognized as a key contribution to the LSC Memorandum of Understanding return. Maybe I have one question referring to the first talk of this session. Is there any discussion or prospect of making this an LVK magazine?
I mean, it has been thought about. So I think the tricky thing is that this is something that's been grown out of the LIGO collaboration. So if this was to be adapted into a LIGO Virgo or a LIGO Virgo Kagra magazine, I think is difficult. It should be a new thing, which is made sort of jointly between the collaborations rather than, yeah, I think if you try to change this magazine into LVK magazine, is at risk of it sort of looking like it's still the LIGO magazine because it wasn't born from all three collaborations. I don't know if Livia also wants to say a little bit about that.
Yeah, I agree with you. And maybe within Virgo and Ego, especially, we are considering the possibility of doing a magazine specific to Ego and Virgo.
Yeah. Sasha?
Hi all, thanks Hannah. That's a really nice talk. We in Upper Reach in LISA we discussed setting up a group to begin with and just discuss our options and see where we go, because we are approaching it from the other end actually as a LIGO magazine where it really grew for a long time. We've got this kind of benchmark now and see if we aim for that or do something different. So I think it would just be nice to gather a small team of people who are interested in this kind of work and just discuss what we should be doing and see if we can come up with an idea which you could present to a consortium and find these authors. And so try to just take it step by step. And we've set up the group. And if you would like to take part in this, it's got an email already. It's lisamagazine@lisamission.org, strangely enough. So please just drop us a line there and see if we can get a kind of critical mass for a team. Thanks.
It's also in the chat. Yes.
Posted in the chat.
Good. Thanks, Sasha. Just to add to that, I think I said it in the talk, but this is really fun it's a nice thing to work on. So you can really have fun with it. So
yes, absolutely.
I encourage people to do it.
And it might sound stressful, but in reality, we always manage to juggle these deadlines and we give ourselves plenty of time. And it's actually easy getting stories. We just approach people after interesting talks or read about some interesting results in a paper. And we just say, hey, don't you want to write maybe a page or 2 pages? And these kind of large feature articles, they more or less determined by these consortium milestones anyway. So we had 03 now. It's going to be 04 commissioning and begin of 04 and so on. And it will be the same in LISA, I'm sure.
Yes, and sometimes we reuse texts also for other purposes, for media, for instance. We have one example from LISA currently, because we did the MFR press release, and Martin Gehler wrote a very good article for LISA. And I'm using this article also for journalists as a background information. So we can always use these texts and also the images for other things.
Yeah, also for web pages and such.
Yeah, yeah.
Okay, thank you. So we are perfectly on time for the next presentation, which is about one of the two future ground-based large projects. It is by Paul Fulda from Florida. Please.
Okay, just let me share slides here. Okay. So thank you for giving me the chance to talk about Cosmic Explorer, which is this concept for next generation ground-based gravitational wave observatory. So let me get right into it. I'm giving this presentation on behalf of the Cosmic Explorer Consortium. So I will talk about several aspects of this concept, a little bit about the actual observatory design, but a bit more about science case. And then since this is the LISA Consortium, the LISA Symposium, I'll try to talk about some of the overlaps that the science case for Cosmic Explorer has with LISA. Okay. So in the title, I call it a next generation ground-based gravitational wave detector. So just a little bit of background on what that really means. So you can kind of broadly separate the detectors and their various incarnations into the initial detector phase, where we had LIGO, Virgo, and Geo 600, for example, along with others. This generation of detectors demonstrated that the technology was feasible for precision laser interferometry on a kilometer scale, and they reached design sensitivity in most cases, but did not detect any gravitational waves. The next generation to come along was the advanced detector generation, like advanced LIGO and advanced Virgo. And these, obviously, as you all well know, have now been enormously successful in detecting 90 gravitational wave events to date, and then with many more to come, surely in 04 and 05. And so what I'm talking about here is the generation beyond, next generation. So that's in the US, the concept there is Cosmic Explorer. In Europe, it's Einstein Telescope, and you may hear about others as well from different parts of the globe. So what does this next generation mean? What's the step forward here? This is slightly different in that we're really considering entirely new facilities now. So not upgrades to existing facilities like the advanced generation, but new facilities. And then in terms of the scope of the science that can be produced, we're talking about moving from sporadic detections to precision observations for detections we do make, and a cosmological survey of sources. So the kind of range we can achieve with detectors of this generation puts us well into the large redshift kind of regime, and we're really doing cosmological science at that point. And as I'll mention a bit more later, there's the timing hopefully works out so we can have contemporaneous observations in multiple bands of the GW spectrum, giving us some good synergy with LISA. So I like to think of this leap from the advanced generation to the next generation as really something like going from the first telescopes to the kind of extremely powerful telescopes that we use to do cosmological science today. Okay, so a bit about where this concept in the US came from. So I think one possible source of this project you can imagine is this paper that was published in 2015, actually just before the first detection, a gravitational wave detector with cosmological reach. So I've just included the kind of the top part of that paper down here. There was a study team assembled in 2018, kind of coalescing around this concept. And the concept was, as I mentioned, not just another LIGO upgrade, but this entirely new facility. So the idea is to think big in a couple of ways. This should be the ultimate facility at least in the US, for ground-based gravitational wave detection. So something that should have a kind of long lifetime and allow for upgrades in terms of detector technology as we go forward. So the first tangible major step here was to produce a horizon study, which was just released in October 2021. So a bit about the Horizon study. So this was an NSF-funded study to inform the scientific community and funding agencies about the project, Cosmic Explorer, while providing a foundation for further development. So what that looks like in practice, there's many aspects covered in this study. A look at the kind of science that's enabled by Cosmic Explorer, this reference concept. So, how many detectors, what size, a little bit about the interferometer technology involved, and then some trade studies in terms of how to best use available resources to get the best science as well. And it does include also a cost estimate for what this project would eventually cost. So at this point, I'd really like to advertise, just take a look at this Horizon study. I think there's a lot of interesting discussion in there. And it would be, I'd also like to encourage you to endorse it, so you can endorse this study. And that, of course, helps to show community support, which is necessary in the long run. Okay, so a bit of an overview about the observatory itself. So what are we really considering here? You'll have seen on the title slide this kind of artist rendering of what a facility might look like. We're talking about an entirely new observatory on the ground, so not underground. Some of you might be familiar with Einstein Telescope, which plans to be built underground. Cosmic Explorer is not intended to be underground. And the reference concept right now is to have two L-shaped interferometers of 40-kilometer arm length for one and 20 kilometer for the other. So the idea behind making the sensitivity like about 10 times better than advanced LIGO or A+, is relatively simple. It's just a matter of scaling up. So as we know, a gravitational wave effect is a strain effect. The bigger the baseline, the bigger the signal that you are trying to measure. So if noise sources stay the same, you make the detector 10 times bigger, you get 10 times better strain sensitivity. It's a little more complicated than that in the details, but this is the basic idea. Just to scale up proven LIGO technology. So this would form, if all goes well, part of a global network, again, operating in tandem with the Einstein Telescope in Europe. Of course, there's major benefits to having global networks in terms of signal localization, source localization, and other confirmations of signals and parameter estimation. So the other thing that I wanted to mention, just to kind of highlight, is that we're not talking about, as I said, a single upgrade. We're talking about a new facility. So this should have room to grow in the future. So we have a baseline concept for how to reach this kind of baseline sensitivity. But the idea is to build the facility with future upgrades in mind, so that as technology progresses in the coming decades, we can take full advantage of that. Okay, so I'm going to get a little bit more into the interferometer concept. So as I mentioned already, most of the sensitivity enhancement we envisage, at least for the first implementation of Cosmic Explorer, just comes from the length. So we're talking about 40-kilometer or 20-kilometer arm lengths compared to the 4-kilometer of advanced LIGO. Having the pair of interferometers with different arm lengths actually helps to avoid the bandwidth limit of only having a 40-kilometer detector. For 40 kilometers, the free spectral range is, I think, 3.75 kilohertz. And so we have a little null, a little dip in the sensitivity at that frequency, and it's actually helpful then to have a second detector with a slightly different null. Keeping things simple is, I think, important at first, so we can reduce technical risk by just using proven A+ technology. So that's 1 micrometer laser, fused silica optics operating at room temperature. And we can still reach an extremely good science return with these proven technologies. On the other hand, there should be a parallel R&D effort towards future or alternative technologies. So for example, 2 micrometer silicon optics, cryogenic operation, with a view to future upgrades or in case we encounter difficulties, unexpected difficulties with the baseline plan. So I'll run a little bit through the noise budget. So you can see the noise budget here on the right, if you know, with various kind of fundamental noise sources. And we can see, so the gray line there shows the total, the sum of all those noise sources. And across the band of interest, there's really 2 fundamentally limiting noise sources. So there's a quantum noise, which is a major limiting noise source, of course, in advanced detectors, but also Newtonian noise, which is something we haven't yet tangled with too much in the advanced generation of detectors. So those are going to be the fundamental limits. Newtonian noise, just by the way, is the direct gravitational coupling of density fluctuations in the environment around the test masses to the test mass position. So you cannot fix this one by having improved suspensions. We need to do things like active cancellation or post-subtraction of Newtonian noise. So just a list here of the assumed technologies in this sensitivity curve that you see here on the right. So we're talking about 40-kilometer arm length for the plot you see there, 320 kilogram test masses. This helps actually a lot with the quantum noise. At the low frequency end, it's radiation pressure noise we're talking about. More massive mirrors are just harder to move by the radiation pressure force, so that helps. Much bigger and much bigger suspensions, so 4 meters long, 1,500 kilogram total mass suspensions for reducing seismic noise at low frequencies, 1.5 megawatt of light power in the arms. We assume 10 dB of frequency dependent squeezing, which actually on a tabletop experiment has just been demonstrated at the AEI for a Michelson. Balanced homodyne readout, like the plan for A+, and about between 10 and 20 dB of Newtonian noise suppression by this methods I mentioned earlier. And at the low frequencies, I think it's important to note that fundamental noises are one thing, but when you get towards the low frequencies, there's a lot of technical noises associated with the various control loops that need to be engaged to keep the interferometer at its operating point. And there's going to need to be a lot of development in that direction too. Okay, so when you're considering a new facility, the site selection, of course, is a critical part of that. And that comes hand in hand with community engagement, actually, in the way we envisage it for Cosmic Explorer. So we'll consider many aspects, of course, environmental noise, the ability to acquire the necessary land, environmental impact, but also a big part of what we want to consider early on, and not as an afterthought, is engagement with local and indigenous communities. So getting this started early, so connecting these communities with Cosmic Explorer, we think in the long term is going to be crucial to the project's success. So this involves many of these aspects you see listed down here. Certainly obtaining local consent for the building. This is going to be a big facility, so it's going to have an impact on the local population. Building these relationships early on and getting people involved in a positive way as much as possible. Another aspect here is that the idea is to operate as an open data facility. So to get the data to the public who paid for it through their taxes early. Okay, so I'm going to move on now and talk a bit about the science objectives of Cosmic Explorer. So these are kind of illustrated in this this circle here, this sort of pie chart. We split it into 3 major science objectives, and I'm going to go through each one briefly. So the first one here is black holes and neutron stars throughout cosmic time. So this illustration on the right, I think is great for getting an idea of the cosmic scale of what we can achieve with these detectors. So on the left, you see these kind of horizons for neutron star in-spiral systems. So those yellow dots are neutron star in-spirals. And you see those horizons corresponding to the different detectors. So Cosmic Explorer is that pink horizon going all the way out to redshift of 10 for neutron stars, and even beyond for 30 plus 30 solar mass black hole binaries. And so what you can see here is actually, by the time you get out to that pink line for the black hole, binaries and the green line for Einstein telescope as well, we're actually capturing signals from almost all the black hole binaries in that mass range in the entire observable universe, which is really quite a leap beyond what we're doing right now. So this, we'll have access to lots of exciting signals there, remnants from the first stars, population 3 stars, get ideas about the formation of supermassive black holes, different formation channels and galaxy formation, and just really conduct a survey of these stellar mass black hole populations. Moving on, the second major science theme is the dynamics of dense matter. And this, of course, mostly comes from the neutron star in spiral signals. So here we see a quantum chromodynamical phase diagram. And excitingly, with detectors like this, we have access to a region of this phase diagram that's just not accessible in any other way. So we're talking here really about precise measurements of neutron star mergers and the post-merger phase. So with high signal to noise measurements of these events, we can really start to probe the dynamics of this dense matter and understand more about the neutron star equation of state and so on. So there's a lot of exciting science to be done by accessing these signals with high precision. And then third, we have the extreme gravity and fundamental physics. So this is really an extension of science that's been done already with advanced LIGO and advanced Virgo, but to the to another level of precision, essentially. So by having more precise, higher SNR measurements of black hole mergers, we can test the strongest gravity here, and even start to pick possibly discount or maybe even prove theories for unusual compact objects like boson stars and so on. And this has implications also for modifications to general relativity or also dark matter and dark energy. So exciting.
Paul, how many more slides? We need some time for discussion.
Okay, I will try to flip through a little faster. So this slide just shows kind of the level of the precision that you could measure GW 150914 with for Cosmic Explorer. Gets an idea of the kind of regime change between the advanced and the next generation detectors. So I'd like to say a bit about synergies with LISA and Cosmic Explorer science. We're looking at black hole binaries in different mass ranges, of course. So LISA is looking at the heavier mass sources. So by combining both, we can really get a better picture of the evolution of black holes throughout time. Yeah, I think there's a lot to be gained by combining observations and data analysis between these. One aspect of synergy we will have heard about before is the idea that LISA sources evolve into the LIGO band. By the time LISA is operating, that should be, in essence, the next generation band. So that can be helpful for EM observations, of course, but also if there's any tuning to be done of ground-based detectors. I think another thing that's worth considering is the same can work the other way around. So there's an interesting paper that I've just mentioned here, where you can actually use triggers from Cosmic Explorer and other next generation detectors to dig out subthreshold events from the LISA data as well. So it's an interesting example of it working the other way around. Okay. Oh, should I?
Time is almost over.
Okay. I'll then finish with just the kind of, I'm going to skip this and just look at the kind of expected timeline going forward. So we're right here at the end of the Horizon study. The next stage will be trying to get a conceptual design together, so more detail for the facility and the interferometers. And then, as that progresses, more detailed designs, and eventually the idea is for construction to begin in the early 2030s, and then all going well, having observations actually coinciding quite well with the start of LISA observations. So I'll probably just leave it there for now then and take any questions.
Thank you. We have quite some questions. David Robertson asks, how do you plan to measure the Newtonian noise to do the subtraction or suppression?
Yeah, that's a good question. So that would be, I think the baseline there is essentially to have an array of seismometers around the test masses, and then to correlate those kind of environmental sensors and subtract from the gravitational wave data stream. But this is an active area of research right now.
Shweta asks, are there planned locations already? Can that be an option?
That is, well, let me answer the first part first. So there have been some sites which have been investigated, but I wouldn't say we have as far as a selected site already. It's too early for that right now. Would Canada be an option? I think that's more of a political question really than a science question. Not one I'm equipped to answer right now.
Asks, what is the main advantage of going to 2 micron?
Yeah, so going to 2 micron allows you to use silicon, crystalline silicon, as the test mass material, which is opaque for 1 micron. And the advantage of silicon is that at cryogenic temperatures, we actually have a zero crossing in the thermal expansion coefficient, and that helps with reducing thermal noise.
And maybe I have also a question. I remember from earlier discussions that with such long arm lengths, there may be an issue with the 2 test masses not hanging parallel anymore because of the curvature of the Earth. Is that something you have to consider?
Yes, in a way. So actually, funnily enough, I do have a slide about this and bonus slides here. So this figure down at the bottom shows the issue you're talking about. So yeah, you're right that we have basically a vertical to longitudinal coupling due to the non-parallel G vector at the end stations. And so what that means, that coupling basically scales linearly with the length. And so for a 10 times longer detector, you have a 10 times stronger coupling. However, of course, the signal goes up by a factor of 10 as well. So you're kind of back where you started. So what this really leads to is a requirement for about a factor of 10 better vertical seismic suppression. And so part of this essentially leads to some impacts on the suspension design, primarily requiring vertical spring blades for the final stage suspension, which is not used in the advanced detectors.
Thank you. More questions? Okay, then let's take 13 minutes of break and start in 1:15 on time, please.
Thank you.
这个屏幕看不到是吧？啊，这个没开，没，那个了吗？还是关了。关了。对。
Hello, John. Can you hear me?
Yeah. Okay. I try. Hello. Hello.
Hello. Would you like an opportunity to share your slides to try?
Yeah. 看看怎么试一下。这是什么 ？Share camera， 对，还是得点 share camera。那上面是开了还是没开？看这个， Wahrnehmung erstmal. Che non succede. Tante posso che anzi. Deve ser succede. Andrew. Yeah. Hi, Andrew.
Hi, this is Valdemar. Is it possible also to quickly check my screen share?
Ganja?
Hi, Valdemar, and to the other speakers as well. I think Andrew may have stepped away from the computer, or maybe he just didn't hear us. Andrew, are you there? Could you stop screen sharing for a moment so that the others can quickly check if they can screen share? I don't think I can enable, disable the screen sharing directly myself, but so we need Andrew to do it. Or let me check. David Robertson, are you there? Maybe they've both gone to get coffee.
I've just returned.
Oh no, excellent. Andrew's back. Yeah, so just while you were away, Andrew, Valdemar was asking about screen sharing, and I know you also invited Professor Leo to screen share, so maybe there's time to do that now.
Yes, certainly. Go ahead.
Yep, looks good. Yeah, we can see this good. This is fine.
Okay.
Valdemar, do you want to try yours next?
Yeah.
So it's very good.
What looks like it's cut away. Somehow not. Can you see the full title? No.
No, the left-hand side is cut off.
Ah, okay, no, it's because it was sliding in. So it should be now the full title.
Yeah, that was good.
Okay, very good.
You want to try?
Ziren, yeah, if Ziren is online, then
yeah, sure. May I have a try?
Yeah, please do.
Valdemar, please stop sharing.
Yeah.
Yeah, someone.
What's the matter here? Sorry. I'm not used to do that on that computer. So, here. Yeah. Okay, should be stopped.
Thank you. Perfect.
All right. Okay, let me try. It's all right. Can everyone see my?
Yes.
Yeah,
okay.
All good.
And Alex Jenkins, maybe?
Yeah, hi. Should I try sharing my screen?
Perfect.
You can see that?
Yeah,
okay?
that's great.
Perfect.
Then still 5 minutes for a coffee. So I hope everybody is coming back.
Yeah, I'm here.
So welcome back. In this second part of the session, we will first have two presentations from the two Chinese projects to build space-based gravitational wave detectors, Tianqin and Taiji. And it is my great pleasure and honor to welcome Luo Jun, Professor Luo Jun, who is an old colleague and a good friend. And he has built the Center for Gravitational Wave Research in Wuhan, which is now the largest center in the world. And then he went on to become the president of the Zhongshan Daxue, Sun Yat-sen University, one of the biggest universities in China. And there he has built the Tianjin Center in Zhuhai, which is a huge, huge center. And now he's not president anymore, I believe, but back full power in Tianjin, I hope. So please.
Yeah, dear Gerhard, dear friend. First of all, I would like to thank the organizer for giving me a chance to introduce our Tianjin project. This is a plan of my talk. Since the first detection of gravitational wave by LIGO, we have iterated the area of use gravitational wave to detect the universe. However, gravitational wave detection is still in its infancy. Most gravitational wave signals and the most part of universe are still out of reach, and many gravitational wave related questions still lack answers. By looking at the spectrum of gravitational waves, one can see that the mini-Hertz sector has the most diverse gravitational wave sources, most diverse distribution of gravitational wave sources in the universe, and the highest detection precision expected, and so is the golden frequency band of gravitational wave detection. To effectively detect the gravitational wave with mini-Hertz frequencies, one needs to use laser interferometer with luminance of at the scale of 100,000 kilometers, and so the detectors must be formed in space. That is, by doing space-based gravitational wave detection. Tianjin is one of several space-based gravitational wave detectors. On this slide, you can see the sun, the yellow ball in the middle of the picture. To the left, you will see the Earth, which is blue. Surrounding the Earth, there are 3 dots marked as spacecraft 1, 2, 3, which form the constellation of Tianjin. When the Tianjin was originally proposed, no one knew when the gravitational wave could be first detected. So the orbital plane of Tianjin had been chosen to face the ultra-compact white dwarf barrier 00806 to maximize the response of Tianjin to this particular source and to let Tianjin detect gravitational waves as soon as possible after its launch. Since the orbital plane is nearly vertical to the ecliptic plane, it looks like a harp in space, and so is the meaning of Tianjin in Chinese. Since Tianjin is using geocentric orbit with a radius of about 100,000 kilometers, its sensitive frequency bands is in the between those of LISA and DISEGO. The detector is also expected to be easy to deploy, track, control, and to communicate with. If everything goes smooth, we expect to launch Tianjin around 2035. Our team started gravitational experiment in early 1980s. In 2000 and 2000, we started to do research on 2 core technologies of space-based gravitational wave detection, inertial sensor and intersatellite laser interferometry. In 2013, the electric static inertial sensor was the first successful test in orbit in China. The Tianqin project was officially proposed in 2014. Since 2016, because of the breakthrough made by LIGO, there has been a lot of attention come to gravitational wave detection. Tianqin project has also picked up momentum. During the past few years, we have carried out 2 major projects in the technology roadmap of the project and have reached important milestones. We expected to reach another milestone in the next 5 years, so-called Tianqin 2 second. On the right one, you can see many types of sources that can be detected by Tianqin. One can notice an important feature here. For different types of sources, the range of detection is different. With such diverse type of sources, one can expect Tianqin to make a huge impact on science in areas including fundamental physics, astrophysics, and cosmology. In the following, I will discuss some issues that have been considered challenges in the mission concept of Tianqin. First, Tianqin will be operating in a complicated gravity field environment. On the left, one can see an illustration of Tianqin in the solar system. Note, the objects are not drawn up to scale. Before Tianqin, no one had tried to use a constellation whose orbit plane is vertical to the eclipse. The presumption was that no stable orbits can be found in such configuration. Through simulations, we have found that not only there exist highly stable orbits, but there are many of them. We are lucky. The key to the solution is that the factor of moon can be minimized when the orbits are vertical to the lunar orbit. Earth is not a perfect sphere, as one may usually assume. In fact, there are significant irregular distribution of mass on Earth, which lead to an irregular distribution to the Earth's gravity field. So, when the Tianqin satellites orbit around the Earth, they are moving in an irregular gravitational field, which can lead to irregular relative motion between the pairs of satellites. Such added irregular motion could interfere with the gravitational wave signals. With the high precision numerical simulation, we have found that there is indeed significant contribution to the acceleration noise expected for the test masses. But fortunately, the Earth's cause acceleration noise decreased steeply around 10 to minus 4 Hertz. It's below the requirement of Tianqin, above 10 to minus 4 Hertz. This means the acceleration noise induced by the Earth's gravity field will not be a fundamental obstacle to Tianqin. The moon will can get in the between the sun and the Earth every month. And so there is a significant chance for moon eclipse. Moon eclipse could cause fast and large variations of sun share on the satellites. And the result, the thermal shock, could cause interruptions to the gravitational wave detection. So it is an issue that one should worry about. We find that by using moon resonant orbits, it is possible to have stable orbits that experience no moon eclipse during the observation times, for example, 5 years. The earliest known challenge issue concerned the Tianqin is the sun radiation. Due to its unique configuration, the orbital plane of Tianqin is nearly fixed in the space, so the sun will evolve around the constellation and passes through the orbital plane of Tianqin every half years. The large variation of the angle of solar radiation is making the thermal environment complicated and challenging. We have recently found that within the detection band of Tianqin, the radiation noise is dominated by the solar constant fluctuation. Of course, this does not mean the problem has been solved. We still need to find a way to deal with the long-term variation of the radiation flux. But now we can mainly focus on the latter problem. A second potentially important challenge for the Tianqin is a solar wind plasma. Due to the long distance in inter-satellite laser propagation, there is a danger that the space plasma could become a significant source of phase noise. That is quite different from LISA. Our preliminary studies show that plasma-induced phase noise is sub-dominant except during the strong magnetic storms. But some study is needed to minimize the potential impact of the space plasma. To sum up this part, several of issues that have been raised as potential problems for Tianqin have been shown to be not difficult to solve. There are still issues like sun radiation and the solar wind plasma. One must study them seriously. Apart from the challenge mentioned so far, the most important challenge comes from technology. In the following, I introduce very briefly the progress we have made with the technology development. To successfully detect a gravitational wave in space, we need to accomplish several key technologies, which I am sure many are familiar with now. We have adopted that 0123 technology roadmap to bring the required technology to maturity. For this, we have planned a few major intermediate projects. Starting from 2016, we have made some important progress with this roadmap. Tianqin satellites are using the geocentric orbit and are not too far from the Earth, so it is possible to use laser range technology to help obtain high precision orbit information, which is helpful in mission scheduling and in data analysis. Because Tianqin is not there yet, we started by doing lunar laser range. Apart from its application in the Tianqin project, lunar laser range is also significantly important in studying the Earth-Moon system and in testing general relativity. Our lunar laser range project officially started in 2016 when it received funds and support from Chinese National Space Agency and the National Science Foundation of China. Our new laser range station was complete in early 2019, and on June 8, 2019, we carried out the first successful range experiment to the moon. On November 7th, 2019, our new station successfully ranged to all 5 radial reflectors on the moon. A preliminary analysis show that statistical errors in most of normal points are better than 1 centimeter.
Roger, we still have 5 minutes, including discussion.
Yeah, okay. In the second mission in the roadmap is a Tianqin-1 experiment satellites. The goal of satellites to test the 6 keen technology in orbit. On December 20, 2000, the satellites have launched and it accomplished on January 21st, 2021. The experiment on the satellites can be roughly divided in 4 planes. Apart from testing the technology of Tianqin first have also collected data and enrolled the first interface on Earth's gravity field. As a short summary, we have get a fruitful result for the Tianqin-1 satellites. The third mission in the roadmap is a Tianqin second experiment satellites, which will be launched around 2026. To support the research of Tianqin, some indicated research facilities have also been built, include the Tianqin Center, Tianjin Range Station, and a cave laboratory and the ground simulation facility. Since the start of Tianqin project, there have been many international experts contributed to the project through many different ways. Here, I would like to express my thanks for all of them. Finally, let us talk about the future plan and the time schedule for the project. During the past years, we have been quite successful having the next research facility in place and in carrying out 2 major milestones. And our Tianqin second will be launched in expected to launch in 2026. After that, we expect the final mission for the Tianqin detector will be officially approved and expected to launch the detector around 2035. Thank you everybody.
Thank you very much. This is truly impressive. There are many technical details that one could discuss for days and not only in 15 minutes. The time is too short. I'm really looking forward for something like a Tianjin Symposium, if that's possible, maybe online, even better in China, but right now it's difficult to travel. But there are many technical things really interesting to discuss. Do we have any particular questions? What is the constellation breathing angle for Tianjin?
Thank you. I hope to have a chance to hold a meeting offline and invite all of you to visit Zhuhai here. We have already the meeting online already, but I hope in the near future.
Yeah, the breathing angle is shown here. It looks smaller, 10 times smaller than these are.
Yeah.
And Olaf,
this object is more stable because it's very, very close to our Earth. I think I don't know the exact the result because our college have numerical simulation about that. What is?
There are 3 more technical questions, but maybe you can discuss them offline. We have to move on to the second presentation by Walter Wren, whom we also know very well. He was a postdoc in Hanover, and he's now in the Taiji project. Please.
We can't hear him.
No, we can see your screen, Walter, but we cannot hear you.
Now can you hear me?
Yes. Very well.
Can you hear me?
Yes.
Can you hear me?
Yes. Yes. Yes.
Okay, great. So this is the outline of my talk because I guess everybody heard a lot about science and the significance of spaceborne detection. So I will skip this and go directly to the Taiji program. And okay, as everybody knows that there are 2 missions in China. One is Tianqin and Professor Lin. I really give a wonderful talk on that. So I'm going to talk a little bit about Taiji. So Taiji consists of 3 satellites, takes the heliocentric orbit, and the other one is 3 million kilometers. And this project is led by the Chinese Academy of Science. And here is the brief history of Taiji. Taiji is initiated by Professor Huan Rui on 2008. After a few years feasibility study, and we obtained a preliminary mission design. And after a few years of technology development, we launched Taiji 1 on 2019. And I will talk a little bit more later. So we keep on the development, and I will tell you the progress. Okay, here is the science Taiji. Taiji has 2 types of primary sources. The first is the intermediate and the supermassive black hole measure. And the second is the intermediate and the extreme mass ratio inspiral. And other sources such as the galactic binary and primary stochastic background, and I will not go into detail here. The science is very promising, but the technology is quite challenging. The first is the so-called inter-satellite laser interferometer, and we needed to reach 1 picometer displacement measurement over millions of kilometers. And the second is drag-free control. We needed to realize super fatal G free falling for the test mass, which is already achieved by Lisa Passbander. So that's why we take 3 steps to realize the final goal. The first is to test the technology on ground, and it contains all, includes the Taiji 1 mission. And the second step is to launch the Taiji Pathfinder, also named Taiji 2, to verify all the technology for Taiji. And step 3 is we hopefully can launch Taiji maybe a few years after 2030. And this is Taiji 1, and it was adopted on 2018 August, and it was launched just 1 year later. So it's very quick mission, and we test quite a lot on this satellite. You can see here is the interferometer and the sensor head of the accelerometer. And we install 2 types of iron thruster. One is RT and the other is Hall. We install 2 lasers just in case, and they both work well on the orbit. And this is the electronics for the sensor, and here is the phase meter. And if you wanted to look into the detail, please refer to this article. So I will talk a little bit more about Taiji 2 and its progress. And what is Taiji 2? Okay, because Taiji 1 is relatively simple, so we need a mission to bridge the Taiji 1 and 3. Taiji 2 is actually one arm of Taiji 3. It consists of 2 satellites. One is master satellite. And okay, so there is one set of measurement system. It contains one inertial sensor, interferometer, and telescope. And for the master satellite, we replace one set of this measurement system to the fiber interferometer to simulate another arm, which we can use to verify the TDI algorithm. For the other satellite, we call the slave satellite. Just to save some money, we replace this set of measurement system with dummy mass. If we have enough money, we may wanted to install another inertial sensor here on the master satellite. So this is a glance of the Taiji 2 satellite constellation. It takes a heliocentric orbit, trailing Earth a little bit about 2 or 10 degrees, depends on the money. And the arm length is 1 million kilometers. So the interferometer developed for the Taiji 2, and we use the optical bond. We build 2 one-to-one model of the interferometer, and we build the link, and they can interfere with each other. And we also test this in the vacuum chamber. This is the phase meter, and the number is quite nice. They can reach 6 picometers, less than 6 picometers. Here is the laser with the fiber amplifier, and this is the FP cavity to stable the frequency of the laser, and we can obtain maximum 4 watts output power of this laser. And here is the primary mirror of the telescope, and it's a small scale. It's only about 100 millimeter, and it's well polished. The flatness is about 100 lambda. And here is the structure of the telescope, and we measured it. The stability is below 10 picometers. It's not that good, but it's enough for Taiji 2. And here, this structure is made of InvaSteel. We built another made of silicon carbide. They are quite similar. And here we also doing a experimental demonstration for the actuation tracking and pointing for Taiji 2. For the actuation, we use a camera, and we use differential wavefront sensing for the pointing. And the scanning pattern is Archimedes spiral. The precision of the actuation is quite nice, but the pointing is not so good because maybe we are doing this experiment in the air. And we also made 2 of the pointing ahead angle mechanism. One is one-dimensional, just fun, a toy model. And we're going to use 2-dimensional PM for Taiji 2. And the longitudinal noise is quite essential for Taiji 2. So we measured it. This is the measure setup. And the number is 8 picometers per square hertz. Not very good, but all right, it's enough for Taiji 2. We also made a prototype of the test mass. It's made of gold and platinum alloy, and this is the cage for the test mass. And we use the quantum machine to measure the parallelism and perpendicularity. And the number gives quite a nice, meets even Taiji 3's requirement. This slide is the electrode for the electronics of the inertial sensor for Taiji 2. And we connect with the sensor head and test the displacement readout. And the noise is below 1.7 nanometer per square hertz. And the driving voltage for the actuation, the fluctuation is below 3 pm. And these numbers are quite nice. So for the drag-free thruster, and because we already flight the iron thrust with Taiji 1 and the wet fine, so here we only focus on the thruster head, and here is the electronics. We build a pendulum to test the noise of the thruster, and this could get thrust just flew yesterday. And finger crossed, we hope it will bring us very good data. And we build a so-called quasi-physical simulator for the drag-free control. We actually see all the box. It has the same electrical interface same as the Taiji 2, and also the same data flow as the Taiji 2. And we simulated the whole process, including the acquisition, such as the scanning pattern. Here, scanning and communication and acquired. And we turn the DWS on different reference sensing, so we can the curve becomes very narrow. And here is we release the test mass, and here we catch the test mass. And now we enter in the science mode, and it's work very nice. So we'll also build a toy model for the satellite, actually just to testify the structure, which we will install this measurement system on this structure. This structure is made of carbon fiber ceramics, and we experimentally measure the coefficient of thermal expansion, and the number gives quite a nice result. The platform, one of the key technology is the thermal control, and we made a thermometer, and the rate of noise is below 30 microkelvin along the interesting band. And we build a small box trying to see how can we control the temperature fluctuation. And here is the heater, and we put the thermometer in, and using the active and passive control. We tested this in a very huge tank, and we can see inside of the box, the fluctuation is very stable, below 30 microkelvin. Okay, this is the positioning stage for the dummy mass, which is used to compensate the gravitational stiffness and also actuate the center mass of the satellite. And the positioning precision is quite nice. It's below 0.1 millimeter. Is good enough for Taiji 2. We also build a full link modeling, which we call the Taiji Simulator. Is a numerical simulator, and it's a very nice platform which we can insert independent module such as the payload and the noise model and etc. And we can use this simulator to fine-tune the mission parameter, trying to find one optimized curve, and trying to maximize the science. And for the data analysis, we already have a GDI numerical simulator, which contains the random noise code ranging and also the frequency noise separation, and the noise model. I mean, subtract the noise from the data pre-processing. For the science data analysis, we are about to release the first round mock Taiji data challenging, and the data set will be released maybe in the recent 1 or 2 months. So finally, the outlooks, we try very hard to catch up with the step of LISA in order to share 1 or 2 years flight time with LISA, and trying to build the LISA Taiji network, which has very a lot of very interesting science, especially we can localize the source in a very precise manner. And a lot of scientists already work on this, and I'm looking forward more to come. That's all my talk. Thank you very much.
Thank you very much, Lothar. That was very impressive. It's really fantastic to see so much progress. And indeed, it would be fantastic to have a Chinese detector at the same time with LISA. That will indeed open a complete new window of science. Do we have any questions? Maybe I have one. You showed a lot of hardware already. How many institutes of the Academy of Science are contributing to the hardware?
Okay, till now, we have more than 30 university and institutes contributed to all the hardwares.
Mm-hmm. Are they in one place, or are they all over the country?
All over the country.
Antoine asks, you mentioned the mock Taiji data challenge. How do you plan to organize it?
Okay, we are actually now, just planning or organizing this challenging, and we prepare already the data, and we now ask one of the group to do the data digging, try to dig out the sources and see whether this data, whether this scheme will work or not. So we wanted to release this data on public, and every group around the whole world can to attend the challenge.
Thank you.
Okay, thank you.
Do you plan to have some international symposium or conference or workshop or something like that?
Yeah, after the COVID things, maybe maybe next year, and I will ask Professor Liang and see how can he organize one of the international symposium.
Martin Henry asks, in addition to the prospect of overlap in operation time with LISA, can you say some more about the expected overlap in frequency?
Okay, I guess the frequency is very much overlapped, almost the same associative frequency band, because we share almost the same arm length. Taiji has 3 millions of kilometers, and LISA has 2.5. So the sensitivity curve is very much overlapped.
Okay, thank you.
Okay, thank you all.
Well, and thank you very much, Lojin and Lothar. It was very encouraging to see, and I wish you the very best for your project and hope to see you more closely soon again.
Yeah, sure.
Here's one more question. What are the RPO and maintenance plan? But I don't know what RPO is.
Sorry, I don't know what is RPO.
Well, then we can move on to the next presentation by Waldemar Martens from ESA about another concept for space-based gravitational wave detection in the future. Please.
Okay. Let me see. Can you hear me and see my screen?
We can hear you. And now we can also see your screen.
Let's see. Okay. Yeah, hello everybody. My name is Waldemar Martens. I'm a member of the LISA study team at ESA and as an orbital mechanics specialist. And today I would like to talk to you about a proposal for a successor mission for LISA called LISA MAX. And this is work done together with my colleague Michael Kahn and Jean-Baptiste Bale. So first, to give you some context, ESA is currently looking into potential future science missions which come after the Cosmic Vision program, which LISA is part of. And that is called Voyage 2050. You've probably heard of it, and covers the time frame 2035 to 2050. And among the themes that have been selected is also gravitational waves, and that has triggered, of course, some more interest and study of potential future mission concepts. In general, if you look at proposals for space-based gravitational wave observatories or projects, they use very similar concept from the orbital mechanics point of view. They always or mostly use triangular constellations using the Lagrange points or using Earth-like orbits or Earth orbits, as we have heard before in the presentations. And they target either a higher sensitivity or new frequency band. And I would like to in particular point out this one proposal, which is a white paper which was submitted to the Voyage 2050 call, which is probably the most similar concept to what I will talk about today by these authors here. So LISA MAX is trying to answer the question, by how much can we actually increase the constellation, so targeting lower frequencies and still be affordable? And the first idea was to use the Sun-Earth Lagrange points 3, 4, 5, and to place constellation there. So just as a reminder, every three-body system like the Sun and the Earth have these Lagrange points, which are stable, fixed points, which means that the forces cancel out there. And it's very convenient that the points 3, 4, and 5 form an equilateral triangle, and would, of course, be a very nice place to put a constellation there. And such a constellation would have an arm length of 259 million kilometers, which is 100 times more than LISA. There's one problem with that. If you place a satellite in L3, seen from Earth, that's right behind the Sun, so you cannot communicate with it directly. You would have to use another satellite as a relay, but that would increase the mission complexity. We chose a slightly simpler solution. We just offset the whole constellation by 10 degrees. To move that satellite away from the Sun. You won't be in the Lagrange point exactly, but the disturbances at this place is still low enough, as we will see. So what you see here is already the fully optimized constellation, which means that the initial states, the position and velocities, have been finely tuned numerically to minimize the breathing of the constellation. So the breathing is the variation of the corner angles and the arm length rate over the mission duration of 10 years, assumed here. And as a reminder, so the corner angles need to be small because the larger the variation of the corner angles, the more the motors need to move to point to the distant spacecraft. And the requirement for the arm length rate comes from the bandwidth limitation of the phase meter. So if the relative velocity is too high between the spacecraft, it will induce Doppler shifts that move the beat node frequency outside the allowed band, which is for LISA between 5 megahertz and 25 megahertz in absolute value. And what we have achieved here, or what can be achieved here for LISA MAX, is much better than what we have for LISA. For LISA, we have typically corner angle variations of ±1 degree and rates of ±10 meters per second. And here we have an improvement of a factor of 10. The corner angles and a factor of 2 for the arm length rates. So such a constellation is really stable, and from the orbital mechanics point of view, it's a good place to put a detector there. Of course, we're interested what a sensitivity curve would look like for such a detector, and for that we need to take a couple of assumptions, which I've summarized here to compute the sensitivity curve. In particular, I want to point to two parameters, which is the laser power and the telescope diameter. The laser power, I've assumed the same as for LISA, 1 watt, although I'm sure that could be increased. For the telescope diameter, if you have an arm length 100 times larger than LISA, then you need to make up for the lower photon density, which is much lower, of course, at that distance. So to fully compensate that, you would need to scale up the telescope by a factor of 10, 3 meters, which is quite large and quite heavy, probably. So for now, we assume a 1 meter telescope, which is probably still large, and it's actually a driver, I think, for this mission concept, the mass of the telescope. So if you look at the sensitivity curve computed in a very simple model for both LISA and LISA Max, you see that there's a reduction of 2 orders of magnitude in the sensitivity. And because I talked before about the laser power and the telescope diameter, so those determine the laser shot noise, and that determines how high or low this point here, this minimum, is actually. So if we increased the telescope diameter or the laser noise, the laser power, that would move us further down here. And actually the telescope diameter enters to the 4th power, whereas the laser power only enters with the 1st power. So the telescope size has a much stronger impact, but it also has a much stronger impact on the mass of the spacecraft. So so with the assumptions taken, we're roughly at the same level as LISA here. And I want to point out that these are sky-averaged sensitivity curves, but LISA Max is bound to the ecliptic. So the constellation normal is always pointing to the ecliptic pole, whereas for LISA we have this cartwheel constellation where the constellation normal is inclined by 60 degrees, and during the course of a year, as the constellation moves around the sun, also the normal moves around the sun. So we get to see different portions of the sky during the course of a year, which we don't have here. Okay, we also looked briefly at different gravitational wave sources, massive black hole binary inspirals. So here you can see the traces that are produced by 2 different masses of black hole binaries, 10 to the 5 solar mass and 10 to the 8 solar masses, during a 4-year mission, which are fully in the LISA band. But if you go to a time much before the merger, 1,000 years or 10,000 years, you see it's no longer in the LISA band, but still in the band of LISA Max. So it's similar what happens between LISA and ground-based detectors, so that the signal goes from one band to the other. And there are surely many more science cases that could be investigated here, but for that I would point you again to the white paper by these authors that have a more clear or more detailed survey of the science case. The next thing that we're interested in is how much mass could we actually bring to this place, to this, to such a constellation. Because I mentioned probably we need large telescopes, and that means we need probably not a joint launch, but dedicated launches for each satellite. So for LISA, we have a joint launch. All 3 satellites are launched on the same rocket. So the final mass, the dry mass of the spacecraft, is a function of 2 things: how much mass can the launcher bring into orbit, and how much fuel do we spend during the transfer. And so that's what we do. We compute the transfer. And what we assume is that we have an Ariane 6-4 rocket, and that it can give us 10 tons at an escape velocity of 1 kilometer per second. So that is very well within the planned capabilities of Ariane 6-4. Probably we will have even more. And by the time we're looking here, probably even higher mass are achievable. So that's a conservative assumption here. But yeah. So the way this transfer works is that either we insert from Earth into a heliocentric orbit with a semi-major axis below the Earth. That will induce a drift. So because the orbit period of the spacecraft is lower, we will drift ahead of the Earth, so this green curve here, And then we drift as long as we, when we reach our destination, we fire our engines, do a braking maneuver, and stop there. And the same, if we want to go into the other direction, we insert into semi-major axis higher than the Earth and drift and do a stop maneuver when we end at our destination. Of course, the braking maneuver, the size of the braking maneuver, and thus the fuel that you spend depends on how fast you go, how many revolutions you do around the sun. So in this plot, you see one revolution around the sun is one of these hops, because this is a rotating frame, right? So the Earth and the sun are always on the x-axis. So one such hop is actually a revolution around the sun. And we found that a good trade-off is like for the two spacecraft that go to L4 and L5 to do one revolution, almost 2 revolutions, and for the other one, almost 4 revolutions. Let's then look at the numbers. So what you see here on the left is the transfer delta V and the arrival mass. So the arrival mass is the function of the transfer delta V and the 10 tons launcher performance that I mentioned earlier. And they're different for the 3 spacecraft, of course, because they take a different course. And they also depend on the launch date because of the Earth eccentricity. So depending where on the Earth orbit we depart, we will have to take a slightly different journey, and that impacts the delta V. And since we want to build all our spacecraft, all the 3 spacecraft identically, what really counts is the minimum here. So between the 3 spacecraft, the minimum mass that can be achieved, and also if we want an all-year launch opportunity, also the minimum over the whole year. And this is like 6.5 tons roughly what we achieve here, with a 10 tons insertion mass. So that's about 3 times the mass of the LISA spacecraft, which is not surprising since we have 3 launches here and LISA has 1 launch and the delta V is very similar. Okay, I want to briefly mention, in the beginning I said that LISA Max is kind of driven by the question, how large can we constellation be while still being affordable? And so I want to briefly look at variations of this concept and see how that would impact the complexity of the mission and the mission cost. So one drawback of this concept is that we are bound to the ecliptic plane. And so the antenna pattern is fixed, although it rotates around the sun. During the course of the year, the plane is always fixed.
Your slide is not updating. You still have the transfer cost on the screen.
Yes. Yeah, I have no slide on that actually. Okay. I'm just trying to. Yeah, so it would be actually nice to have a out of ecliptic constellation, but to achieve that, we would actually need a much higher delta V. So just imagine the velocity of the Earth is 30 kilometers per second on its orbit. If you want to significantly change that velocity, you need delta V's of the order of many kilometers per second, so much higher than here. So this is completely infeasible to achieve out of ecliptic constellation just with propulsive maneuvers. What could be done is similar to what is done for the Solar Orbiter mission. So that mission uses combined flybys between Earth and Venus to increase the inclination with respect to the ecliptic to observe the sun from the poles essentially. And a similar concept could of course be done here, but again, this increases the complexity because it's much more complex trajectory, much longer, much more expensive operations, and so on. So yeah, another option that could be considered to go beyond the Earth or the Earth-like orbit, like for instance to a Mars-like orbit, and put spacecraft in the Lagrange points there, for instance. But again, this has large impact on the mission complexity because the delta V is again much higher. You're essentially looking at 3 Mars missions there. Yeah, so it is feasible, but it has a large impact on the cost. So that's why I try to argue that kind of this concept is the maximum constellation that we can achieve while still being more or less affordable. Okay, just quickly on the transfer duration. Yeah, so with the transfer that we chose, we have 2 years for the 2 spacecraft that go to L4 and L5, and 4.5 years transfer. So the one that goes almost behind the sun. Okay, to conclude, yeah, so I've presented LISA Max, which is an observatory proposal, which lowers the sensitivity by 2 orders of magnitude, so makes it much more sensitive in the microhertz band. The main benefits, of course, that it opens a new band for gravitational wave observations. Compared to LISA, the constellation is more stable. So we have lighter requirements on the optical assembly and tracking mechanism, so the one that's sensitive for the breathing angles, and also lighter requirements for the frequency planning. The main challenges are that we probably need a much larger telescope and higher instrument mass. So if the telescope is a factor of 3 larger, the mass is probably a factor of 10 or so. We therefore might need 3 dedicated launches, which translates into higher cost. The constellation acquisition will be also much more complex, because to find a spacecraft that is 100 times further away than in LISA, you need to know exactly where it is. We have no omnidirectional sky coverage due to the fixed constellation plane. And okay, things that could be looked at in the future: how can we make the telescope smaller or lighter, and maybe bring them to a joint launch to reduce mission cost, and maybe increase the laser power, which could partly compensate for a smaller telescope. Okay, that's it from my side. Thank you.
Thank you very much. That's very interesting. Do we have questions? I don't see any yet.
Here, a hand by Stefano.
Ah, yes, Stefano, yes.
Hi, nice talk, interesting. Actually, we are thinking to this tank very actively in the context of the follow-up on Voyage to 2050. I'd like to ask one thing. Below 10 to the minus 4 hertz, the acceleration noise we have measured in LISA Pathfinder goes up quite rapidly.
Yeah.
And we also have a hint that below, say, 20 microhertz it steps up even more fast due to temperature fluctuation. How much this will spoil your science case?
Yeah, I mean, this is something, as I said, this is a very simple model. It has an impact on both curves, right? Because also the LISA curve doesn't take that into account here. We have just a constant acceleration noise here. But yeah, this will go up steeper, as you say.
Yeah. And at high frequency, what about the confusion noise? Due to the binary in the galaxy.
Yeah, I guess there are people who can answer that better than I can. I don't know.
Never mind. Thank you. Very interesting. Thank you.
Stefano has already asked Guido's question. More questions? Well, maybe one from me. I'm sure you are perfectly aware of that. There are other noise sources you have to consider which also scale with the arm lengths, like laser frequency noise, laser intensity noise, and many others. So what is the plan to, and you also know there are tools, tables, and simulators, for example, from Simon Bartel. So do you plan to refine the noise model? Or certainly you do, but any concrete plan?
We have no concrete plans. I mean, it would be, the first step would be to see how this concept actually compares with different proposals and see whether it's worth studying, because currently it's not an official either activity. It's just done essentially in our free time. So yeah, if there's more interest, then certainly we can, I think, especially with Jean-Baptiste and the software that, the simulation software that they have, it would be no problem to increase the fidelity of those noise models.
Jean-Baptiste answers the galactic confusion question. It probably does limit the sensitivity gain, but more binaries will also be resolved than in LISA.
Mm-hmm. Why is that? The frequency resolution is, well, never mind.
Maybe also the data analysis techniques will have progressed a lot by then. Okay, thank you. Then we are perfectly in time for the final talk of this session. It's about another technique to detect microhertz gravitational waves from Alex Jenkins. Please.
Hi, thanks very much. Can you see my slides, my cursor?
Yes, we can.
Yes, we can.
Brilliant. So yeah, thank you to the organizers for giving me a chance to talk today. My name's Alex Jenkins. I'm a postdoc at University College London. I'm going to be talking about these two papers, which came out last year. I worked with my collaborator, Diego Blas, who's based in Barcelona. And the concept here is a bit different. So we're looking at ways of detecting gravitational waves, in particular stochastic gravitational waves in the microhertz frequency band, but using binary systems as detectors of these gravitational waves. So rather than being sources of gravitational waves, we want to look at these binaries, measure their orbits very precisely, and see how the orbits respond to the presence of a gravitational wave background. So I'm going to start by talking about stochastic backgrounds in general, although I'm sure that many members of the audience already know a lot about this. And then I'll talk about this binary resonance phenomenon in particular, and then I'll describe our results of this study. So by stochastic background, I mean a signal which looks something like this in the bottom right-hand corner of this diagram. This is just a neat way of thinking about different possible gravitational wave signals you could see. And here we're talking about a signal which is persistent, so it's always on, and it's phase unmodeled. So we don't have like a coherent template we could use to search for it. So in a sense, it's sort of the opposite of the compact binary coalescences that have been detected by LIGO and Virgo so far. And you could get a signal like this essentially from superimposing the gravitational wave emission from many faint or numerous sources which can't be individually resolved. These sources could be astrophysical, like distant compact binaries, or they could be cosmological. You know, you could think about stochastic backgrounds from inflation or from cosmological phase transitions. And that's something I'm going to pick up later in this talk as well. And we characterize these backgrounds in terms of this density parameter. So this is essentially saying how much of the universe's energy budget is taken up by gravitational waves in a given logarithmic frequency bin. So I'm going to show everything in terms of this quantity omega GW rather than in terms of the strain. So in order to motivate why we want to think about these microhertz searches, I want to quickly give a super quick overview of existing constraints on the stochastic background. So we have two key techniques for doing this at the moment. We have ground-based interferometers, such as LIGO and Virgo, and we have pulsar timing arrays. And both of these at the moment rely on looking at how gravitational waves change the flight time of photons. So going to this plot here, I'm showing this omega GW quantity. You can see that on the right, this is the most up-to-date constraints on this from the first 3 observing runs of LIGO and Virgo. And on the left, I'm showing a representative sensitivity curve from one of the pulsar timing arrays. This one is from the Australian Parkes pulsar timing array. So you can see that these are both, very impressive levels of sensitivity. We're measuring, or we're sensitive to parts per billion of the universe's energy density in these two particular frequency bands, but there's a huge gulf in between them at the moment. There are a couple of constraints which exist in between currently. I'm not going to talk about these in detail, but you can see that from a cosmological perspective, they're not particularly interesting because they only tell us that you can't have more than, say, 1% of the universe's energy density in gravitational waves, but that would be pretty enormous in cosmological terms. You can place a better constraint from early universe observations. So essentially from using CMB and Big Bang nucleosynthesis observations to tell us how quickly the universe was expanding at early times, because there's a contribution to that expansion rate, which comes from the energy density of gravitational waves. This curve that I've drawn here is a bit different from the others in that it's not frequency specific. This is a constraint on the integral of omega GW over this huge frequency range. So treat this with a bit of caution. And it's also only relevant for gravitational waves which were around at those early times. So gravitational waves coming from coalescing binaries wouldn't be part of this. Okay, so that's the present situation. But if I fast forward to the future, obviously we're all very excited by the science that will be possible with LISA, which is going to sit in this gap between the ground-based interferometers and the pulsar timing arrays. There's also going to be obviously updated ground-based interferometers such as Einstein Telescope or Cosmic Explorer. There'll be better pulsar timing arrays, for example, with the square kilometer array. We've heard a bit earlier on about potential interferometers which could sit in the band sort of in between the ground-based interferometers and LISA. And there's also proposals for atom interferometry experiments which would sit in that band as well. But even with all of these exciting new experiments, you can see that there's still a very significant gap here in the microhertz regime. So we're interested in looking at ways of filling this because there could be all kinds of interesting gravitational wave signals waiting for us there. Okay, so the proposal here is to look at the resonant effects of gravitational waves on binary systems. So what I mean by this is you can imagine you have your two objects which are orbiting around each other, and just like any pair of test masses, the proper distance between them oscillates when a gravitational wave comes past. If you try to measure that oscillation directly, that's extremely challenging, but you can have a dynamical effect where if the frequency of the gravitational wave is some integer n divided by the period of the orbit, then you can have this resonance where every time the binary is at the same phase of its orbit, the gravitational wave is having the same force on it. So for example, if it always gets pushed when it's at this point and pulled when it's at this point, and that repeats over many, many orbits, you can have an effect which accumulates and gives you something which is much easier to observe than the kind of direct instantaneous oscillations. So this is why it's very useful to have a stochastic background, which is always on, because it means that you're constantly hitting this system with gravitational waves. And so you are able to accumulate a signal over time. So this idea was not new to us. It's actually something similar is mentioned in the classic textbook by Meisner, Thorne, and Wheeler. And they're very dismissive about this idea, saying that the sensitivity isn't good enough to make it interesting. But this doesn't account for that resonant phenomenon that I was just talking about, which makes the signal much more easily detectable. There were also some, there was a paper by Lamhui et al. Back in 2012, where they looked at this idea and applied it to a particular binary pulsar system. And also some recent ideas were used by my collaborator Diego to look for, rather than gravitational waves, similar effects that can come when you have a coherently oscillating ultralight dark matter field, and how that can have resonant perturbations on binaries as well. So we thought, in light of these more recent developments, we wanted to go away and really calculate what is the most sensitivity gain that you can get from this technique. So the challenging thing with the stochastic background is that you don't know exactly what the strain is doing at any given point in time. It's a random process. And so that means that this randomness propagates into the orbit of the binary. So rather than having a model for how the orbit evolves over time, we need to have a model for how the probability distribution of the orbital elements will change over time. And this is what we do. We're able to evolve this distribution forwards using this equation called the Fokker-Planck equation. This is a well-known tool from many other fields of physics, where essentially we can calculate a diffusion rate and a drift rate in terms of how this distribution evolves, and write this down explicitly in terms of the omega GW, the strength of the gravitational wave background, at each of the resonant frequencies of the binary. So this figure on the left is just an illustration of how, rather than thinking about all of the many, many possible different random trajectories you could take through parameter space, we instead focus on this picture where you think about the probability distribution of all of the possible different outcomes and look at how that changes over time. If you're interested in playing around with this, the code is open source and available on GitHub, and you can evolve your favorite binary forwards in time very quickly and easily. And this is just an example of the output. So each of the little panels here is a figure which is showing, if you think about the covariance matrix between all of the different orbital elements, as the randomness propagates into the orbit, the uncertainty grows. And so typically the values of this covariance matrix gets larger. But you can see that we're able to capture some interesting physics and how they all evolve differently. Some of them grow linearly, some of them grow quadratically because they're sourced by the linear terms. Some of them have this weird oscillatory behavior for this particular system. That's because of the pericenter precession. But all of this is encapsulated in the code that we've developed. Okay, so that's the sort of science of what's going on, but now I want to talk about how we actually apply this and calculate some forecasts for what the sensitivity would be for particular binaries. So there's two probes that we're thinking about in particular. There's timing of binary pulsars, which can give you very precise measurements of the orbits of these systems, and also lunar and satellite laser ranging. So bouncing lasers off of retroreflectors, which were left on the moon, or which are on man-made satellites orbiting around the Earth, which can give you measurements of how far away these things are from the Earth down to the level of millimeters, and so give you a very accurate picture of what the orbits are and what they're doing over time. I think the really nice thing about this is that these data, they already have very exciting and very well-developed science cases, regardless of the stuff that we're talking about today. And so these data will be taken anyway. In a sense, the analyses that we're proposing aren't adding any extra cost. It's just a case of looking at this existing data and analyzing it in a different way to get the gravitational wave constraints for free. So, okay, this is the same figure that I had before, but I've now added the forecast constraints from our method. So there's three different colors here. In red, I have combined constraint from many different binary pulsar systems. In blue, I have the constraint which comes from lunar laser ranging. And in green, I have the constraint which comes from satellite laser ranging with the Lagios satellite. All of the solid curves indicate forecasts for what should be possible with existing data, present day data. Whereas the dashed curves indicate what we expect the sensitivity to be by the end of the 2030s. So roughly, you can think by the time that LISA is coming to the end of its nominal 4-year lifespan. And you can see that in particular with lunar laser ranging, we can get some very interesting cosmologically relevant constraints in pretty much at 1 microhertz. So just to flash up I showed the curve on the previous slide, which came from binary pulsar systems. This figure here is just showing how that comes from combining all of these different constraints from different systems. We went through the ATNF catalog, which contains information about many, hundreds of different binary pulsars. But you can see that the constraints here are driven by just a handful of systems, including at the high frequency end, the Hulse-Taylor system and the double pulsar, these well-known systems. But you can see that going to longer periods and therefore lower frequencies, we typically get stronger constraints. Okay, so here's the same figure again. It's even more crowded now because I've added some signals which might be lurking in this frequency band. I just want to focus on two in particular. So the purple and pink dotted curves, these are to do with the possible signal, the so-called common process signal, which has been detected first by Nanograv and now by all of the main pulsar timing array collaborations. So this is not yet confirmed 100% as a gravitational wave signal. For that, we would need to see the kind of cross correlations between the pulsars that would be indicative of a Hellingsdown correlation. But if it is a gravitational wave signal, you can see that at the sort of steepest spectral indices that are allowed by the Nanograv data, that this would even intersect with the lunar laser ranging constraints that should be possible with present data. If you're more conservative and you fix the spectral index to be that which you would expect from inspiraling massive black hole binaries, you can see that this still intersects with the lunar laser ranging curve for the end of the 2030s. So this could give us some really interesting information about this supermassive binary black hole population. So just one other signal that I want to focus on, I've drawn these two yellow dotted curves here, which are possible signals from cosmological phase transitions. And you can see that these are particularly interesting for us because they're quite strongly peaked. And so with this curve here, I'm kind of showing an example where you can sneak it in between LISA and the pulsar timing arrays. So this is an example of a signal which we could be particularly useful for in setting a constraint in this microhertz gap. So just briefly, these cosmological phase transitions, a generic prediction of very many theories of particle physics beyond the standard model. And I just want to characterize them in terms of these 4 parameters, because on the next slide, I'm going to show you the constraints we can put in this parameter space. So this transition happens at a given temperature, a given epoch in the early universe. There's some strength parameter alpha, which tells you how loud the signal is. There's some rate parameter beta, which tells you basically how many Hubble times it takes for these bubbles to nucleate and collide with each other. And there's a bubble wall velocity, which also affects the strength of the signal. And these peak at a frequency which it's not too difficult to get this frequency to fall in the microhertz band. So here, this is I'm getting very near the end, I promise. This is a diagram showing the parameter space that I was just talking about. And in particular, I want to highlight these blue exclusion regions here, which are those coming from lunar laser ranging. And you can see that there is a region of parameter space which gets eaten out by this, which wouldn't be touched by either LISA or by pulsar timing arrays. So this is just demonstrating a concrete model, a concrete region of parameter space where our methods could tell us something that existing or planned experiments couldn't. So that's it. Thank you very much for listening. I hope I've convinced you that this is an interesting technique that we could use to learn about gravitational waves in the microhertz region. Thanks for listening.
Thank you. Very interesting. Questions, please. Stefano applauds.
So may I also ask a question?
Yes, please.
So when you say you put an upper limit from one of this technique, lunar laser ranging or whatever, you're taking their noise as the limit?
Yeah, so it's a combination of, on the one side, it's our model for, you take a given gravitational wave signal and you compute what is the size of the effect on the orbit that you expect. So how much deviation should we get in the orbital elements? And then you combine that with, from the lunar laser ranging experiments, what their uncertainty is, basically on the ranging distance. And we perform a Fisher analysis to tell us, for a given ranging distance uncertainty, what uncertainty there then is on each of the orbital elements.
And what do you do with the binary pulsar? What do you
with the binary pulsars? It's very similar. So there's a well-known paper by, I'm trying to remember who it is. I think it's Blandford and maybe Damore, I can't remember, but yeah, essentially taking the timing formula for the expected times of arrival of the pulses, which is the your observable, and then you can take derivatives of that with respect to each of the different orbital elements to tell you, essentially your sensitivity to each of those.
Mm-hmm. Thank you.
Thanks very much.
Thank you. Do we have more questions? No. Then I would like to thank all the speakers in this session, which was a very fruitful and fascinating session. And see you again in a little more than 1 hour for the final plenary. Bye-bye.